Hey folks, this is Björn from the Bavarian R2 Builders. D-O is a Star Wars droid from Rise of Skywalker. A gentleman by the name of Michael Baddeley created a version that you can 3D print at home, and the Bavarian Builders expanded and improved that version significantly and call the result D Ov2Evo. The link to Michael's Patreon, where you can get the original print files as well as our improved version, is in the description. This is the second in a series of tutorials for building D Ov2Evo. Thanks for joining, let's dive in.
This time we're looking at the electronics. And before we go into the individual groups, let me give you an overview over what we put in there. So on the main chassis installed, we have the power distribution board, which also has a voltage and amp meter that can be read via I2C. It has a fuse, it has a battery input plug here that gets distributed to the 4 output plugs, and it has a small 12-volt regulator to power 2 optional motor cooling fans. To this we connect 2 battery packs. These are 18650 batteries. You can get them everywhere. These are basically a lithium ion, and they get connected because each one of these packs gives about 8.2 volts when fully charged. They get connected in series using this cable. Then we have the main IMU here. That is an ISM 330 DHCX on an Adafruit breakout board that gets connected up here. We have the amplifier. We have the main brain of the system, that is a Arduino Maker Wi-Fi 1010. So small form factor, but a relatively powerful Arduino, much more powerful than the 328 Arduino Uno or Mega that gets used in the original design. To this we connect an XB for radio control. We connect a small MP3 player module. That's a standard MP3 player module like you find in many builds. And we connect a maker shield to control Dynamixel servos. This maker shield gets powered by not straight the battery power, 16 volts, that would be a bit too much. It goes through a voltage regulator. It's one of these. You can get them from AliExpress, a dime a dozen. So this provides 12-volt regulated power for the Dynamixel. The Dynamixel that we're using in the body is this one here. It is an XL430 W250T. The XL and W basically say something about the torque that the servo has in the gearbox, and the T talks about TTL. So this we talk to this on a serial cable. It already has the printed gear, main neck gear installed on there. The main electronics get mounted on this main board. This is Felix's design, just like the power distribution is. This takes the Arduino here, it takes the XB over here, it takes the MP3 player module here, and the output for the MP3 player module, the 2 channels are up here. This bit you can ignore. That's just a fuse for an optional power amplifier, but we're not using that. We're using a much smaller amplifier, so we don't need that stuff. This is the output port for the power to which we are going to connect the servo shield. And this is the power cable that goes out the bottom, that gets plugged into the power distribution board. Also on the bottom we have 2 7-pin connectors. 4 of these pins are going to be used for the motor encoders, and 3 are going to be used to provide the motor signal itself. And then on the top we have 2 I2C plug outputs. So to this we're going to connect the I2C bus on the main module, and then also in the neck. Talking about the neck real quick, this is the main axle. It's counterweight just a bit, so it's filled with lead, and it has a 10-pin connector on one side, and to this we solder the I2C cable and the Dynamixel cable. So this is all that goes up to the neck. One I2C for some external breakout boards up there, and the Dynamixel cable to talk to the Dynamixels in the head. And then last but not least, the main motors. We have already the motor assembly here. So what you see here is the main motor. That's a Pololu medium strength motor with a 20.4 to 1 gearbox. And that motor is fitted with an encoder. So we need this encoder for the control algorithms. And that has 6 output cables. 4 of these output cables, everything from green, the green, blue, yellow, and white, go directly to the main board. So because this is the encoder connection, it has power, it has ground, and it has 2 encoder signals. And the other 2, the red and the black wire, those are the actual motor power. And that gets routed through these tiny little motor control boards. You can get these from AliExpress as well. They have a DRV8871 H-bridge on there. There's also an Adafruit version that's a bit more expensive, but hopefully a bit better quality. So that provides power to the motors. It gets main battery power, so we're powering it directly from 16 point whatever volts. And then it has a 3-prong cable that goes to the main board, which provides the ground connection and the 2 PWM connections that we use to drive the motor slower, faster, backwards and forwards. Please note that this is a 4-pin connector. It also has a pin here that we're not using. This pin is VCC, but interestingly, it's not VCC from the Arduino to the board. It's this VCC. So, and this has 16 volts. So please don't plug anything in there that would fry the electronics. Okay, first up, let's talk about the power distribution board. So what we have here is the power distribution board itself. This cable goes to the batteries. It connects the plus connector of one of the batteries. No, sorry, it connects the minus connector of one of the batteries to the plus connector of the other battery. And then it connects the plus connector from battery 1 directly to the board, and the minus connector from battery 2 goes through the switch into the board. Please make sure this uses XT30 connectors. Please make sure that you always remember that the square end gets plus, the round end gets minus. The square end gets plus, the round end gets minus. The battery packs consist of a printed part that slides into the body. The battery packs consist of a printed part that slides into the body and a bought part that takes the actual batteries. Again, you can get this on AliExpress or on Amazon. Before you put this into the body, there's some preparation to be made. Down here, these 2 contacts must be bridged. So they're bridging the plus from one battery to the minus of the other battery. And then up here, this XT30 connector is soldered on a small breakout board that you can also get a dime a dozen at Ali or at Amazon. And this is just soldered onto the connector is just soldered onto the board. It gets the plus onto the square end from this battery and the minus on the round end from the other battery. Each battery has something like 3.7-ish, realistically 4.1 volts if everything is fully charged. So each of these batteries give you about 16 point something volts when they're fully charged, and connecting them in series should give you a full voltage of 16 something volts. which we're going to try out right now. So let's look at the connector. We have not plugged anything in yet. Okay, we're switched off. So we have nothing. That is good. There we go. We're at 16.3 volts. And if we switch the switch off, we have nothing, which is also good. So let's put this into the body. Okay, now that we have it in the body, let's do a quick cross check. Nothing just yet. Once we switch it on, we get 16.3 volts, hopefully on all of the connectors. There you go. And before we're done with the body, we take the main gyro, plug it into the back socket header, and fix it nice and tight on the front with M2.3 screws. Make sure that this is parallel with the board. Depending on the standoffs you use, there may be a little gap here. So that's it for the main board. All right, next up, we'll be looking at the main next servo. It's this guy here. And we'll test it and we'll give it the right ID. We'll give it the right baud rate. And we will move it to its 0 position. So I've already connected the main board to the power distribution. So if you switch on, you see that it lights up, the fan starts spinning. Now we want to connect the servo to any one of these 3 connectors. I've populated 2 here. You can populate all 3. They're all the same bus, so there's no difference between them. You can use either of them. Okay, this is the servo, and it has a little LED here that will tell us if there's actually power getting to it. So if we switch that on, you see that LED switches for a second. Good. So once we've done this,
we need to connect our Arduino to USB and use the Arduino IDE to flash a sketch called Dynamixel Test that you'll find in the Arduino Utilities folder of the software distribution. You'll find the link to the software in the description of this video. I've already flashed this on here. Connecting the Arduino and opening the serial monitor, you will see a help text appear. We will use this application to configure the servo. There's also an application built by Robotics themselves, the makers of Dynamixel, and you can use it for the same purpose. By the way, in all of these applications, typing help gives you some instructions. The servo won't react until it has power, so let's switch on the main power on the droid. First of all, we need to initialize and scan the bus at the baud rate the servo reacts to. By default, this is 57,600 baud. We will set the servo to 1 million baud later, and anyway, if it doesn't react to one baud rate, try another. Here we'll type init 57,600 into the message bar and see if it reacts to that. The Arduino scans the bus and it finds the servo at ID 1, which is great. We don't want the servo at 57,600 baud though, so let's type set_baud 1 million. Make sure you get your zeros right and hit return. The application tells us this worked, and also that we may want to reinitialize with 1 million baud now to be able to talk to the servo. So let's type init 1 million, and it detects this. Now let's see whether we can move the servo around. Let's move it to 45 degrees just for kicks by typing move 145. That worked. Now let's move it back to origin with move 180. Please note I made a mistake here by moving it to 0. Move it to 180, as that is the center position for all of the servos in this droid.
All right, before we move on to assembling and testing our motors, allow me to say a couple of words about our sponsor, PCBWay. PCBWay offers an impressively comprehensive set of services for makers. Obviously, PCB assembly in a host of different materials, but also PCB creation with SMD and through-hole components, and 3D services like 3D printing, milling, sheet metal assembly, and even injection molding. We've been working with PCBWay since relatively recently, but it has been a fantastic experience with very responsive, friendly, and constructive contact. And they've even offered to sponsor us so that we can make electronics for DO, or remote controls, and future solutions available to you guys faster and cheaper. Very highly recommended for all of your constructive needs. Also, PCBWay is currently hosting their regular project design contest. It's the 7th time they do this. The idea is to foster innovation in open source electronics, and they offer prizes to the winners, including cash, PCBWay coupons, and maker products. So if you're currently building something that you would like to submit, you'll find the link to participate in the description of this video. Fingers crossed that your entry is going to be among the winners. Okay, next up, we want to connect and test the two motor assemblies. So to reiterate, these have 6 cable connections. One of them, white, yellow, blue, and green, goes into a separate cable. This is the encoder. And the pinout at the board is blue, green, yellow, white. The rest of the 2 connections, red and black, they're powering the motor itself. These go into the output of the motor controller. The power input for the motor controller gets powered directly from the battery. And then we have a control connection here that has white as the ground and red and black as the two PWM motor inputs. So the way this gets connected to the main board, and we'll do it just ad hoc here before screwing everything down, is there's these two pin headers down here, and you can use a non reversible pin connector if you have one. I didn't have one. It's relatively simple. You can mark it with a pen if you want to. So this cable, the encoder cable, gets connected to the pin header so that the blue connection is at the very end. And then this one gets connected so that the white connection goes directly next to the other white connection. So if you want to review this, this is how it should look like. And it's all documented in the wiki as well. So if in doubt, please refer to that. So this goes for motor 1, and the same with the same polarity, also with blue at the very top, and then the two white connections next to each other at the bottom. Okay, and to be able to test the motors turning, we need to connect them to the power distribution board. So again, I'll just do this ad hoc here, and later we can clean it up. These both go in here. Okay. So next up, in order to test this, we want to go over to the code again.
We use a different application this time. It's again in Arduino Utilities, and it's called DC Motor Test. I've pre-flashed it here, so let's connect the Arduino. The connection is made, but it doesn't talk to us, so let's type help and hit return. So this application is a bit more complex, since we will use it for motor speed and position controller tuning later. In this case, we will only get the motors turning quickly and see that the encoders are giving us the correct values. The help text gives some commands at the top, and down below you see parameters that we change with the set command. So the first thing we do is we tell it to use both motors. We do this by typing set use motor 3. It should reply with OK. Ignore the other stuff. This application is intended to be used in a proper terminal program, not Arduino serial monitor, so we're seeing a lot of command line indicator output that would normally be hidden. Now, there's another tool hidden in the Arduino environment, and it's called the serial plotter. You can find it up in the Tools menu next to the serial monitor. Let's open that up. Before we even move the motors actively, we are going to check that the encoders work. Our motor speed output is set to 0, so we can just type start, and the Arduino will start filling the output with the goal, which is 0, and the output of both encoders. We are in speed mode, so if the motors are at rest, the encoder output will be 0, but if we turn them with pliers, we should see output depending on how fast we turn them. So let's take our pliers and give the motor shafts a good twist. Okay, both encoders seem to work, that's good. Let's give the motors a positive output. This program lets us change the set point while the output is running by just entering a number and hitting return. We are in PWM mode, so our units are the direct pulse width output from the Arduino, which can go from 0 to 255. Let's go for approximately the middle ground here and just enter 140. This should get both motors turning. As you see, both encoders ramp up pretty quickly, although not quite to the same speed value. This is also a great way to check your motor connections. With positive PWM, both motors should give positive encoder output. If any motor gives encoder values in the opposite direction, reverse the polarity of the red and black leads at the output of the motor controller.
Okay, and we're closing in on to the end of the video. So I've put the main board on top of the holder, routed all the cables. The motors are connected on the underside down there, like we've just seen when everything was apart. The motor drivers seat in these little brackets here on the side. You can see that you can pull them in and out. That's just a friction fit. We have the servo connected. This cable goes to the servo in the neck, or in the body that turns the neck, and from that servo it goes onto this connector, because this is a serial path, so this is basically just routed through. We have the I2C cable connected. This I2C cable goes down to the IMU, and from the IMU, the I2C cable goes into the neck, onto the neck connector. So the rest is as you've seen. What you want to make sure is that you have the cables. It's not as nicely routed as the last one that you've seen when Felix and I built Felix's, but you want the cables all nicely cable tied out of the way so that you can slide the battery boxes in, which is what we're going to do now. So connect, and then these slide in, and they grasp onto, see these rails here, they grasp onto the side brackets and onto the notch in here. So these should be grasped fairly tightly, and you can see you can slide it in with a bit of friction. One goes in there. That concludes the end of the electronics assembly. I'll just do a very quick run through the self-test.
So what the self-test is doing,
I am Dodo,
accompanied by some pretty horrible voice output, is it checks that it can talk to IMU and voltmeter, calibrates the IMU.
Self-test starting. Please stand clear. IMU. Calibrating.
Initializes all servos and runs both motors to check power and encoders.
Power. Okay. Servos. Okay. Left motor. Okay. Right motor. Okay.
And this concludes part 2 of our tutorial on D Ov2Evo. Thank you very much for watching, and please follow and subscribe for part 3 of the tutorial, in which we will add the wheels, test and tune the motor speed controllers and the balancing controller. Prosit from the Bavarian builders, and see you next time.